Hi everyone, I'm Kashyap, and I'm going to be presenting a new generative simulator called SLEDGE. Simulation is super useful in autonomous driving, and it's primarily used with graphics-based simulators like Parla, which have problems with realism and are expensive to design because you need to hire artists to build these virtual worlds. An alternative is log replay-based simulation, with simulators like Nuplan and Waymax, giving the ability to record data in the real world and convert this to a simple simulation environment. Unfortunately, the routes you can simulate in this sort of simulator are very restricted, both in length and duration, and the type of turns you can take, since you need to closely follow what happened in the original recording to have reasonable traffic behaviors. What we present here is a generative model-based simulator where this model generates scenes that match the distribution of the real world, but you can also simulate for arbitrary route lengths, since you can generate realistic traffic along different portions of the route, even if this is not exactly observed in a training log. This type of simulator is also really compact. Downloading a generative model is only like a few gigabytes of storage, as opposed to log replay simulators, which typically have terabytes worth of data logs. So how does this work? Well, the entities that you need to simulate are typically vectorized. It looks like something on the left, where you have bounding boxes for things like vehicles and objects, and polylines for things like lanes and traffic light control regions. We rasterize everything into optical flow maps of two channels each, which looks like something you see on the right here, and input this rasterized scene flow, which has 12 channels, into a ResNet encoder, generating a spatial latent map of dimension 8 by 8. The latent map is separated into certain channels for static lane elements and other channels for the dynamic agents. And this separation enables controllability and selective conditioning, as we'll see later. These latent maps are passed through a learned decoder, which, given some learned queries, can generate vectorized entities again from the original format used in the vectorized simulation environments. And this entire setup closely matches detection transformers or DETR and is trained with the Hungarian matching loss objectives used in these type of architectures. Once you have a autoencoder, the next step in building this sort of simulator is having a diffusion model. Specifically, we use a diffusion transformer, which iteratively denoises random initialized latent maps into ones that fit in the training distribution. Once you have a denoised latent map, you can pass it through the decoder that you trained in the previous step to retrieve this vectorized representation that is compatible with the standard simulation environment that normally operates on logs. The only difference is that you have the generative model substituting for these logs now. To generate long routes, as I mentioned in the beginning, we can start by generating a single tile from this diffusion model and outpaint this tile by essentially conditioning on the observed subregion within a new tile and generating the rest conditioned on that observed part. And doing this iteratively lets us further expand the route to really long lengths. So with this, we build these sort of simulation environments where on the left you see conditioned on a lane graph, we can generate realistic traffic agents. And on the right, you can see that we generate both lane graphs and traffic agents with our generative model. Importantly, the traffic in these environments is reactive and controlled by a rule-based policy called the intelligent driver model. So if you're curious about our work, visit our project page or come see us at our poster. Thank you.